And let me start sharing the screen. Okay. Yeah, so we are almost at the end of chapter 3 in the book, and you should start reading it. Again, as I mentioned earlier, we will have an exam like at the end of this month, like in the last month. So this will be based on chapters 2 and 3, and whatever we cover within this month. Okay, and I have also posted the homework.
Sir, can you repeat? My network got cut off.
So what I'm saying is, that we will have we will have the exam, the exam on at the end of this month, right? Which is sort of understood. I've already told that. So, and I've also posted the homework problem. So please go through that, and also the material will be whatever we cover till the end of this month. So which includes this homework problem and perhaps a little bit more. So I will include more homework problems based on that. Okay. So let's get started. So radiation reaction force. Okay, so we know that any accelerating charge produces radiation, and that must result in the loss of energy of the accelerating charge. Okay, so there must be a force. So if you have a charge, say an electron, which is accelerating and moving, it sort of emits radiation, right? So it must lose energy, and it must lose energy because there must be some force which is opposite to the direction of its which sort of reduces its kinetic energy. So there must be some radiation force that stops the motion of this particle, and hence the energy, whatever energy goes into this radiation must come from the kinetic energy of this particle. Okay, so we want to actually motivate what is the form of this radiation force. Now this is actually a very difficult and still sort of open problem to understand what is meant by radiation reaction force, because if you have an electron and if we consider it to be a point charge, right, so we are basically doing is calculating the EM fields because of the point charge itself, and calculating the force due to that field acting on the charge itself. So it's actually a hard and non-trivial calculation. Here we will actually just give you some heuristic motivation for the form of this force. Okay, so the actual treatment has to be done in quantum electrodynamics, and it sort of involves much more sophisticated techniques like the renormalization. But we will actually not do that. What we will do is we will do some classical treatment. So let's see. So let's consider this charged particle. Let's first estimate what is the time scale. So time scale. The time scale for energy loss of the electron of the particle due to radiation, right? What is this? This time scale is nothing but the kinetic energy of this particle divided by E dot, the E dot due to Larmor formula. So we are actually assuming a non-relativistic particle, right? So what is this? So this is half mu squared, and the Larmor formula is 2/3 E square U dot square, which is A square by C cube. right? So this is the time scale over which an electron which is accelerating is expected to uh, lose its orbital kinetic energy. Okay, so this would be what? So we can actually, this is an order of magnitude estimate. So we can actually write it as u by u dot squared times, and so let me just write this down. C divided by 2/3 E squared by mc squared. So I've actually just rewritten this formula in a slightly different form. So this is nothing but, right, so what is this? Do you sort of,
There's
do
a
you
factor of
recall
2
this?
missing, I think.
Huh?
There's a
Yeah,
factor of
yeah. So just ignore this factor of 2. I'm not, this is an order of magnitude calculation. Okay, and I'm just retaining this 2/3 because quantities are defined like that. I will have 2/3 in some quantities like the standard definition. But what is it? E square by mc square, does it remind you of something?
R naught.
Yes, this is R naught, the classical radius of the electron. So this is nothing but the light crossing time across the size of an electron. Okay, so this is nothing which we call tau. And this is what? U by u dot. This is some sort of a time scale for the particle orbit, right? So suppose your electron is making an orbit, right, on a time scale of TP. So this is nothing but like TP squared, okay? And this is tau. Now this tau is actually a fundamental constant, and this is equal to 2/3 just a second. Let me not forget order unity factors, because this is a definition. This is equal to, sorry, this is tau inverse, right? This is radius divided by velocity, so this should be 1 by time. So tau is equal to 2/3 E squared by mc cube. And if you plug things for the electron, this comes out to be 10 to the minus 23 seconds. Right, of course, it has to be, right? The light crossing time across an electron has to be extremely small. So basically what this means is that this is equal to Tp by tau times Tp, which is much bigger than Tp, right? Whereas this tau is small. So for typical orbits and so on, this is very, very big. So basically what it means is that the energy loss time scale is long compared to the periodic motion time scale. So you can actually almost treat it perturbatively. So you can actually treat the electron to be almost going around in its orbit, but it only very, very slowly loses its energy, and loses its energy. So you can actually treat most of the time this perturbatively. This force is small. This radiation force for typical conditions is small. Okay. So this is good to know. Right. So and this is nothing but R naught by C. And you retain this factor 2/3. Okay, good. Now, how do we derive this form of this force that we anticipate must be acting on this electron in order to slow it down? How do we get that? Okay, so let's say minus f rad dot u. Okay, is work done by radiation force, reaction force per unit time. right? So this force will retard, will slow down the particle. So this is F dot V, and the force has to be opposite to the velocity. So this whole thing is positive. So work done by this force on the charge, basically work should be done by the charge, and because of that it should lose its energy. And we know that this has to be equal to the the power that's radiated out per unit time. Let's see, which we know this is 2/3 E square U dot squared by C cube. So this is nothing but power radiated. So this we know from the energy principle, that whatever the radiation force that's acting on it, it should oppose the, it should act in the opposite direction. So this term should be positive, and this should be equal to the power radiated. So whatever work that the radiation force does on the particle comes out as energy. This is like an energy conservation. Okay. Now, but you see that the left hand side depends on U, right? So this is different in different inertial frames, right? Because U is different in different inertial frames, whereas this is the same in different inertial frames. So this F rad, whatever it is, it does not look like it will be independent of the inertial frame. So this is not the physical, this is not correct. So classically the interpretation of F rad is basically in a time average sense. In the sense that if you consider, right, if you consider some integral like this from time t1 to t2, this is the total work done by the particle in its motion, some periodic motion we can assume. This is equal to 2/3 E squared by C cube integral U dot U dot dt, right? Right. So what I'm doing is, I said here that this force expression cannot be true instantaneously, because this force turns out to be dependent on which reference frame you're using, which is not which inertial reference frame that you're using, right? The forces, we know that should be the same in all reference frames, in all inertial reference frames. But what we say that, we will actually interpret this in a time average sense, and we are just sort of integrating it. Now this term is nothing but, we can actually simplify this using integration by parts. So this is U dot U, right? So this is the first term when you take limits from t1 to t2 minus integral U dot U double dot dt. Right, what I'm doing is just integrating by parts. So one of them can be treated as du dt. So the first term is U dot, and then you retain this and then take a derivative of the other term, which gives you this. Now you see, now the expressions are somewhat similar, so we bring them on the same side. Okay, so what we assume is this goes to 0, right? This assumption is justified by saying that particle is has identical motion at times t1 and t2. Right, basically some sort of a periodic motion, right? So that, you know, when you evaluate this at those times, this becomes 0. I mean, we are imagining some periodic motion. It's clear from here. Okay, now this becomes f. If we set that to 0, f rad minus 2/3 e squared by c cube u double dot dot u dt is equal to 0, right? We have just taken it on that side, or brought it on the right hand side, and we have this. So basically what this says is that we can actually take f rad, the radiation force, to be equal to 2/3 e squared by c cube u double dot. So this is the derivative of acceleration, right? This is rate of change of acceleration. And this is actually also called jerk. So the classical radiation force can be taken to be proportional to the jerk. And this is nothing but, you recall we defined, you know, it's important to know this definition. This will be used multiple times. So we see that 2/3 e squared by c cube is nothing but m tau. So this is equal to, let me just write with m tau u double dot. So this is the radiation reaction force. And again, as I said, the interpretation is classical. This is not a rigorous calculation. A rigorous calculation should actually have to treat it quantum mechanically. It's really, you know, quite complicated. But for our purposes, where we are actually treating radiation classically, this is fine. Okay, and the idea is that this force should slow down the particle, and that is what appears out as radiation. So whenever you have energy loss, there has to be force, right? Because force does the work. Okay, so this is about radiation reaction force. What about so is there any question here? I mean, this is, you know, this is not the most satisfying derivation, but this is just more like a physical argument. Okay, this is, you know, this is ultimately what we need, and this cannot be interpreted in an instantaneous sense, right? It is sort of like an average force, because we assume, you know, we made these assumptions, and, you know, we essentially got it out of a energy argument. Okay. Now, what we are actually going to do is, previously we learned about Thomson scattering. Now we'll do radiation from harmonically bound particle. Okay, so in case of Thomson scattering, the electron was free. Now it is harmonically bound. For example, in an orbit, in a stable orbit, right? So the force acting on in a stable orbit can actually, you can think of it as, if you perturb it, it will do harmonic oscillations. Okay, so this is a classical model. So classical model for line emission. Right, so emission happens in these emission lines. This harmonically bound particle model is the classical model for that. Okay, so let's see. So, you know, you assume that X is some harmonic displacement of a harmonic oscillation. So what is the equation for for such an oscillation? So let's just write this down. So minus tau x triple dot. So first let me write it down and then talk about it. X triple dot plus omega naught squared x equal to 0. I know this is just the equation of motion for the displacement in harmonic oscillator. Here, this is the radiation. This is the radiation force. You see this. So x dot. So u equals x dot, and u double dot is equal to x triple dot. So we are actually considering 1D motion. So F rad per unit mass, which is basically the acceleration. This is an equation in terms of acceleration, is equal to tau x triple dot, right? So this is basically the equation is x double dot equals acceleration, right? So this is acceleration due to radiation force, and when we bring it on the left hand side, it appears with minus sign. So this is the radiation force. Okay, good. But we said that tau is typically much less than the orbital time. Okay, so this is sort of like a perturbation, a small perturbation, right? So, and we know, if this is the dominant equation, we know how the solutions look like. We know that x is sort of like given as x. X is a function of time, so x is like e to the alpha t, where to zeroth order alpha equals plus minus iota omega naught, right? These are just the standard oscillations, but you will have perturbative terms like this. Okay, so plus order omega naught tau terms, right? Because omega naught tau is small, right? So omega naught, this is of order omega naught inverse, right? The particle orbits are on time scale omega naught. Okay, so basically you have simple harmonic motion, but small perturbation due to this. So this x triple dot actually can be approximated as right. So we can actually just write it as a minus omega naught squared x dot, right? Because time variation of x is essentially e to the plus minus I omega naught. So if you take a double derivative of that, you just pull out minus omega naught squared. Okay, so this is like because of this smallness of omega naught tau. So this can actually, this triple derivative term actually can be replaced by a single derivative term, and then it actually looks very similar to our classical damped oscillator. So let me actually write it down. So this becomes x double dot plus omega naught squared tau x dot plus omega naught squared x equal to 0, right? So this is our standard damped harmonic oscillator, right? It's clear, right? How we can go from here to replace this by this, because the dominant term or dominant temporal behavior is just simple harmonic motion. So this term is actually small, so you can actually you will not make a make an error within this order. Okay. So how do we solve it? We know the solution, right? So let's assume some initial condition. So x naught is equal to some amplitude and x dot naught, which is the velocity at t equal to 0, right? If it is a triple dot equation, you need 3 initial conditions, but if it is a second order equation, you just need 2. And let's just take this to be 0, which is, or of order omega naught tau, right? So this is actually small. To leading order, something which is omega naught tau is close to 0. So this is the initial condition, okay, for this oscillator. And what is the solution? We all know this. The solution is solution for xt, right? This is equal to x naught e to the minus gamma t by 2 times cos omega naught t. So you see at t equal to 0, x equals x naught, so it satisfies this boundary condition. X dot is equal to so there will be 2 terms. One will be x naught omega e to the minus gamma t by 2 and omega naught t, and then there will be a smaller term, which is the second one, plus x naught cos omega naught t and minus gamma by 2 e to the minus gamma t by 2, right? So this term is actually this term, yeah, so at t equal to 0, so x dot 0 is equal to, so this term is 0. The second term is x naught gamma by 2, this one. And let me tell what gamma is. Gamma is equal to omega naught squared tau. So this is the definition of gamma. Right, so this is gamma, this is this, basically this coefficient. And we know that this is equal to, in terms of 2/3 e squared omega naught squared by mc cubed, right? So this is just from the expression for tau, and there is omega naught squared here. And you see this is tau. This is omega naught. This is tau times, this is omega naught squared tau. So this is actually, about 0 in the limit, in this limit that gamma is much less than omega naught, which is true, right? So this, this satisfies this initial condition. That's why there was this approximate sign. So this is of order omega naught.
Sir, the x dot does not reduce to the equal to 0 case, right?
What does not reduce?
The x dot. X dot, like
exactly
there will be this
0. It's not exactly 0. It is very close to 0. Of order.
Okay.
Right. So this is what? So this is x naught times omega naught squared tau, which is equal to x naught omega naught tau, and this is actually tiny.
Okay. So up to like that first order.
Yes. So this is actually a perturbative calculation. So that's why we can take it to be 0 to that order. So what is our solution? Our solution is let me just write it down. So this is so xt is equal to x naught by 2 e to the minus gamma t by 2 e to the I omega naught t plus e to the minus I omega naught t. I've just written the cosine here in terms of this. So this is my solution. Now what about, this is fine, but we are also interested in the Fourier, right? The whole point of this model is actually to look at the frequency response. So we want to get this, right? The Fourier coefficient of xt, right? And this is nothing but 1 by 2 pi, right? This is the definition of this. So this is xt e to the I omega t dt, right? So in this case, so what we are assuming, so this is true for t greater than or equal to 0, and for t less than 0, this is 0. Right? This is set to motion at t equals 0. So this integral, right? And yeah, so this, the other thing is we know about Fourier coefficients that x minus omega is equal to x hat omega star. Right, so if we know the Fourier coefficient for omega greater than 0, we know about the negative frequency. So we really are concerned about omega greater than 0, because the negative part is trivially known. If the signal is real, which it is, right? If this is real signal, so this is what we have, and this is nothing but 1 by 2 pi integral 0 to infinity x naught by 2 e to the iota omega naught minus gamma by 2 t plus e to the minus iota omega naught minus gamma by 2 t e to the I omega t dt. So this is your Fourier transform. Okay, so basically you have to put these limits 0 to infinity. This integral is trivial, right? You have e to the I omega plus omega naught minus gamma by 2. So what you get is actually this x naught by 4 pi 1 by gamma by 2 minus iota omega plus omega naught plus 1 by gamma by 2 minus iota omega minus omega naught. So this is your Fourier transform. Now you have put the limit 0 to infinity. So the infinity part gives you 0 because e to the minus gamma by 2 infinity gives you 0. But the 0 part gives you these two terms. So this is your x tilde omega. These are your Fourier coefficient in here in the frequency space. Let me create a little more space. Okay, good. But as I said, this is the standard natural oscillations of a damped harmonic oscillator, and we know that the amplitude is quite high, close to omega equals omega naught, and we are actually considering positive frequencies. So we can actually just approximate it, right? We know this thing. We know the shape of this response. So let me just consider omega greater than 0, and we'll actually consider only this term, because this term will become important only at negative frequency. So your x at omega can actually be written as x naught by 4 pi 1 by gamma by 2 minus iota omega minus omega naught. I mean, the same thing will happen at omega equals minus omega naught, but It's identical. Its treatment is identical. So this is the Fourier coefficient. What about Fourier amplitude square? That's equal to x naught by 4 pi squared 1 by omega minus omega naught squared plus gamma by 2 squared. Okay. So basically, this is your power in your displacement in the Fourier space. Okay, and we can actually write it in a we can actually, if you recall, there was a dipole formula, dipole radiation formula in the frequency space was dw d omega is equal to 8 pi by 3 d at omega squared omega to the 4 c cube, right? So if you recall, when we were doing dipole formula, we actually looked at how the power is distributed in frequency, and this is what we got, right? So what is d? D hat is nothing but E times x hat, because if you have a single charge, you multiply the charge of the electron times the displacement, that's what you get. So basically, this for the particular case will be given by 8 pi by 3 c cube E squared x naught squared by 4 pi squared times 1 by omega minus omega naught square plus gamma by 2 the whole square. I just sort of substituted E times x hat in place of d hat, and this is what I get, which is fine. We can even write it in a more illustrative form as half k x naught squared. What is half k x naught squared for an oscillator? It is just the energy stored in the oscillator with amplitude x naught, right, times gamma by 2 pi, gamma by 2 pi. Let me actually write down and then give the interpretation. Omega minus omega naught squared plus gamma by gamma by 2 the whole square. Okay, now this is sort of like a line profile phi omega, and it's normalized. This is just a Lorentzian line profile, and this is normalized such that pi omega d omega equals 1 over all frequencies. Okay, so what does it mean? And what about this k x naught square? Like if we compare it, right, we can actually read off just by comparing this expression and that expression. We can read off what k should be, right? For harmonic oscillator, k equals m omega naught squared. And what the interpretation is, W, which is the total energy of the oscillator, is dW d omega. This will turn, if this is normalized to unity, this will just be half k x naught squared. So what it means is that an oscillator will emit all its energy if it radiates forever. Okay, so this is the Lorentzian profile of a line. And so this is basically, this is also called, this is natural broadening of a line. And this is like unavoidable minimum broadening of a line, of a spectral line, right? So let me actually just draw it. So you have the peak in this emission is at omega naught, right? And it has a Lorentzian profile, and the width of this profile, the place where it becomes half. So this is like 1. This is like 1, and where it becomes half of its value, of its peak value, that's where the full width is equal to gamma. So you can actually see from this, right? At omega equals omega naught, this has an amplitude which is so when omega minus omega naught is equal to gamma by 2, that's when it becomes half of its peak value. So this is the full width at half maximum. And this is the Lorentzian line profile. Okay, so this is the classic, and this broadening is fundamental. You cannot avoid it. It's because of this radiation reaction force, or it is also connected to the fact that there is this uncertainty principle which make these lines, these energy levels somewhat fuzzy rather than perfect because of the energy time uncertainty relation, right? So delta E delta T has to be greater than or equal to h by 2 pi. So because of a finite temporal width, there's also a finite spectral width for these lines. Okay, so this is the well-known Lorentz profile for spectral lines. Okay, so when you have like energy levels 1 and 2, there will be, the electron jumps from level 2 to 1, emitting an electron, right? And the frequency distribution of these electrons will actually be given by this Lorentzian profile. Okay, and again, this what is, this is in terms of frequency. What about delta lambda? What is this wavelength width in the wavelength space, right? So a lot of times you make spectra in the wavelength space. This is nothing but 2 pi c delta omega by omega, right? So basically delta lambda by lambda is equal to delta omega by omega, and this, right? So delta omega by omega is this, and this is right. So delta lambda equals lambda delta omega by omega. Sorry, delta omega squared. Right, that's what I was wondering. So, so this is delta omega, and what is lambda? Lambda equals c by nu, right? Which is equal to c by so nu is omega by 2 pi, right? So this is what you get. And what is this? This delta omega is equal to gamma, right? This delta omega, the full width half maximum of this line profile is equal to gamma. So this is equal to 2 pi c gamma by omega naught squared. What was gamma here? Right, it was proportional to omega naught squared. So that omega naught squared drops out, and what we have is 2 pi c tau. Okay, And this is just fundamental, you know, this is just, this quantity is just constructed out of fundamental constants, which is equal to 2 pi e squared omega naught, no, omega naught goes away, e squared by mc squared. And this is, you know, if you plug in the numbers, this is equal to 1.2 times 10 to the minus 4 angstroms. So this is actually quite small. This is like in gamma rays, so very, very small. So natural broadening is small compared to, you know, for example, the lambda in the visible wavelength is 5,000 angstrom. Right, so delta lambda by lambda is like 10 to the minus 4 plus 3, 7, minus 8. So it's very, very small. So delta lambda by lambda is small. So this is like the universal broadening due to radiation reaction. Okay. So this is the classical model for line emission. Any question here? Okay, so we'll go to next page. What about, so this was about spontaneous emission. Basically, there was no, so this was like a natural oscillator, so there is no driving. But we treated scattering in the last class. So there we have driving, right? You have an external radiation which is driving the electron, and that gets accelerated and emits. So now if we have, so now we consider driven bound particles. So this is not just spontaneous emission. We are actually sort of considering scattering, right? Because, you know, scattering is nothing but you have a background light which is exciting the particles, and because of their acceleration they emit. Of motion here, let's write down the equation of motion, mx double dot. So this is ma equals the force acting on the particle. So this is minus m omega naught squared x plus m tau x triple dot plus e naught cos omega naught t. So basically this is the situation. So you have an electric field which is varying with omega naught, and you have an electron or a particle. You know, this is excited by this electric field, and you know this electron will oscillate, and it will actually emit radiation. This is scattering. You know, this is harmonic oscillator model for scattering, driven harmonic oscillator. Okay. So what do we have? The equation is x double dot minus tau x triple dot plus omega naught squared x equals e naught by m e to the I omega t. So, you know, now we have, you know, we are just treating this cos omega t with e to the I functions, and you know, if you want to go to real space, all we have to do is take the real part. So now x is a complex number. Okay. Now again, we can actually, you know, if you are, so no, e to the I, sorry, this is not omega naught. Let me actually correct things a little bit. Omega naught is the natural frequency. Omega is the driving frequency. This is actually not omega naught. This is actually omega. Omega is the frequency at which the background field which is exciting this electron varies, and omega naught is the natural frequency of this electron. So basically this electron is in some sort of a bound orbit where it is, oscillating. It's not free. Okay, so this is scattering due to bound particles. Okay. Right, so like in the last time, we can actually replace this term by omega naught squared tau x dot. This whole term actually becomes this. Okay, or we can actually even treat it like that. It's not a problem, and it really doesn't make any difference. Okay, so what we'll actually do is what we'll get does not really depend all that much on this damping term. So let me how do we solve this? We all know that we can write x equals x naught e to the I omega t, where x naught is a complex number, and we can actually write it as x naught, the real number, now e to the I omega t plus delta. Okay, so now this is a phase. Okay, now if we substitute our form, this form, into this equation, what do we get? We get, this is x double dot. We get, we get the solution actually. What do we get? We get x naught equals minus e naught by m divided by omega squared minus omega naught squared plus, sorry, minus iota omega cube tau. Okay, this is what we get. I mean, this is the steady state solution, right? Steady state solution, in the sense that I mean, we are looking at the solution at late times, so then it will evolve in this way. This is the steady state solution. After some time, that it is exposed to this electric field. Okay, so right, so how do we get this? This just becomes minus omega squared x. This is so minus tau x triple dot is equal to minus tau iota omega cube x naught. This is equal to minus tau minus iota omega cube x naught, which is equal to iota tau omega cube x naught. This is just omega naught squared. Sorry, this is no, this is not x naught. This is x, right? Because it just the act of doing a time derivative just brings out an I omega in the front, right? If you do d dt of this, it just pulls out I omega. Right. So this is that. So we have minus omega squared plus iota tau omega cube plus omega squared times x equals e naught by m e to the I omega t. Right, so this gives you this amplitude. If we write this as x naught e to the I omega t, now here x naught is a complex number, so what we get is this, which is nothing but what I wrote there, right? So this is my complex amplitude. Okay, and what about this phase? This delta is equal to tan inverse. This is the phase, this phase of my x relative to the electric field that it's being exposed to. This is equal to omega cube tau divided by omega squared minus omega naught squared. You know, this is trivial, right? This is, I mean, you can just write this as an amplitude e to the I delta, and you know, if you multiply and divide by the complex conjugate of this, you can actually read off this. Yeah, this is standard complex numbers. Okay, so this is your phase. Okay, so there is a phase shift because of this non-zero, you know, because of this tau. So what about the power radiated in this case? So power radiated is equal to, we know the dipole formula, E square x naught square omega 4 by 3c cube. Oops. Right, so that factor 2 goes away because we are sort of averaging over a sort of sine squared variation. So this 2/3 e square a square by c cube becomes 1/3 because you're averaging over sinusoidal oscillations. Does anyone have a question?
Yes, sir. Hello, sir.
Yes, yes, please. First tell me.
Sir, I am Sipravata.
Yes.
Sir, I think in the equation where after the writing x not equal to the value, the second equation there should be an omega naught square. Both the omega square and omega square plus minus should be cancelled. That one should be omega naught square, the natural frequency.
Yeah, yeah. So this is omega naught squared now. Oh, you're saying this one.
Yes, sir. In the
Right.
E by E naught.
As I said, it really won't matter. You can actually just write it as omega. See this term.
No, sir.
No,
You have
what
done a writing mistake.
Huh?
Yeah, in the
Where
third
is it?
line from the bottom.
1, 2, 3. Yeah. Sorry. That's the problem. Which one should be negative?
Yeah,
Okay.
you're doing the correct thing. The last one on the right will
Last
be
one is omega naught. Okay.
and it will be minus I tau omega cube.
No. It will be plus because you know this is correct.
Okay. No, sir. It is minus sign multiplied by the lower one. Correct. You have taken minus in E naught by M.
Oh yeah. So.
Oh yeah. So it will be plus. Yeah. Correct. Yeah. No. Yeah. Yeah. It
Yeah.
is plus. Yeah.
The only problem was this omega naught. Yeah, but anyway, this is like standard driven oscillator. Okay, so this is your power formula, and if we plug in our x naught from here, what is it? So what is our x naught amplitude? X naught amplitude. So this is the full complex number. X naught amplitude is equal to E naught by M divided by omega naught, omega minus omega naught square plus omega cube tau square. Right, so this is the amplitude of this x naught. So we need that here, but we'll need the square, so that is fine. So if we plug that in, what do we get? We get e to the 4 e naught square by 3 m square c cube omega to the 4 divided by omega minus omega naught squared plus omega cube tau square. See, this term is negligible everywhere except omega equals omega naught, right? This tau term, right? When omega equals omega naught, this becomes 0, so we have to have this term. So that's why, you know, this omega cube might as well be replaced by omega naught cube. Oh, sorry, this square root will not be there because I have to take the square. Okay, so this is my power, and we know that sigma, the cross section, the scattering cross section is nothing but power divided by the Poynting flux. Right, the Poynting flux, right? The Poynting flux, we know, Poynting flux of this wave, this incident wave, S, is equal to C by 8 pi E naught square, right? So if we just divide this by this Poynting flux, what do we get? We get 8 pi. Let me just write down the expression and then let me tell what that should be. So what we get is sigma t, the Thomson scattering cross section. If you recall, this was nothing but 8 pi by 3 r naught square sigma t, and r naught was E squared by mc squared. So we will have like E4 m square C4, that's there. And then we have omega 4 by omega square minus omega naught squared, the whole square, plus omega cube tau whole square. Okay, so this is your how the scattering cross section, scattering by a bound, scattering by forced oscillator, right? So previously we were actually, when we did Thomson scattering previously, we considered omega naught equal to 0, basically a free electron, Thomson. But here we are actually allowing the electron to be bound within a molecule, for example, so that it has its natural frequency, which is non-zero. So this is how the scattering cross section looks like, and let's just sort of look at various limits. Right. So limits. What are the various limits? We can go to omega much bigger than omega naught. Right. In this limit, you are shining a light which has much higher frequency than the natural frequency of the electrons. So it really doesn't matter whether the particle is bound or not, right? If you're shining a light which has very high frequency, it will oscillate at that high frequency. In that case, your sigma omega is equal to, if you put this, basically you have sigma t, which is just Thomson scattering, which is independent. The scattering cross section is independent of frequency. The second regime is when omega is much less than omega naught. Right. In this case, your oscillation that is shining, the light that is shining has low frequency compared to this electron, which is oscillating very, very fast, right? So omega naught is much bigger. So what happens in this case is the electric field that's externally imposed is seen almost like a static electric field, static field limit. Okay, and the electron doesn't oscillate. Of course, when you have a driven oscillator in steady state, oscillations are always happening at the frequency at which you're shining the light. So in this case, if you look at this expression, your sigma is equal to sigma t omega by omega naught to the 4. Again, we are like not close to the resonance. You're not close to omega equals omega naught. Right, so in this case, this is Rayleigh scattering. Right, which is because of scattering due to electrons bound within molecules. This is not due to free electrons. So now actually, so this is the second limit. What is the Rayleigh scattering limit? So frequency is much less than the natural frequency. So it's almost like a static limit. For omega close to omega naught, like near resonance, what happens in that case? So we can actually write omega naught, omega square minus omega naught square equals omega minus omega naught times omega plus omega naught, which is nothing but twice omega naught times omega minus omega naught. So your sigma omega, right? We are basically replacing omega by omega naught everywhere except where omega minus omega naught appears. So this is equal to, just a second. So this is equal to sigma t, and what do we have? Right, so this basically is what we are approximating. So wherever there is omega, we replace it by omega naught. So this will be omega naught squared. This is, let me just write it down, omega naught 4 by omega minus omega naught square 4 omega naught squared plus omega naught cube tau square. Right, so what we have? We have, right, recall gamma is equal to omega naught square tau. So what do we have? We have pi sigma t by 2 tau gamma by 2 pi divided by omega minus omega naught squared plus gamma by 2 whole square. Let's see if we get that. Right. So this is what? Omega naught gamma square. So this is 4, that comes down, that gives you omega by, gamma by 2 the whole square. This is omega minus, so right, and I substitute for omega, so omega naught square gets cancelled. There's square here in this case. This also cancels. So what we have is omega naught squared by omega minus omega naught squared, that, and then we just define omega naught squared as gamma divided by tau. So we have something like this. Again, this is the Lorentzian, normalized Lorentzian line profile. Yeah, exactly like the natural oscillator, right, without driving. So basically what it means is that for the cross section has a Lorentzian shape near resonance, just like for natural oscillations. Okay, so this is one thing. So this is your sigma omega. This again, this is Lorentzian, so this is normalized. So this function phi omega d omega, if you integrate, this should give you 1. Okay. So what about sigma? Integral 0 to infinity sigma omega d omega. If we integrate this, what do we get? We get pi sigma t by 2 tau. Right, so what was tau, if you recall? Tau was this light crossing time, right? So this was c by r naught, and there was some 2 by 3 somewhere I am forgetting, and sigma t was nothing but 8 pi by 3 r naught squared. So if we write everything in terms of fundamental constants, you get 2 pi squared e squared by mc. This is E. Right, and right, so let me actually, this is fine, and we can actually also define phi can actually also be defined in terms of nu. So phi nu d nu, if you have frequency rather than angular frequency, that should actually be 1. So if we do that, then let's see what happens. So so phi nu should actually be gamma by 2 pi nu minus nu naught squared plus gamma. Right. So so frequency omega equals nu by 2 pi. So there will be like these factors of 2 pi here and there, because so there will be a 1 by 2 pi squared right, let me just call this tau star. So sometimes we can also use this phi nu, the line profile in the frequency space rather than the omega space. Okay, and if you put in the numbers, you will actually see that phi nu d nu, right? It's exactly the same calculation but done in nu instead of omega. You get pi e squared by mc. Of course, these two just differ by a factor of 2 pi. You can actually see, right? So this is sometimes this factor is very, very common when you look at the atomic physics calculations, pi e squared by mc. Okay, and so basically this quantifies the strength of line, and also, you know, stronger the line, the more is scattering. And you know, sometimes people use this for more, you know, this was just for some simple line, but you can actually generalize this for all lines and include some correction here. So Mn. Suppose you have some energy level M and there is some energy level N and there is a transition. Okay, so you have this prefactor which is exactly the same as in this simple harmonic calculation we did, but you have this factor which is called the oscillator strength, right? And it actually represents, you know, like how many oscillators. This is sort of like a degeneracy. So people do like quantum calculations, right? But in the end, they express their results in classical language by giving these oscillator strengths for various transitions. The quantum calculations are extremely involved, but they can in the end be written, you know, what you need in the end for your purposes is this oscillator strength. Okay, so that's why it's actually important to know this harmonic oscillator model for line formation. Okay, so one last thing that I wanted to draw actually was this oops. What did it do? Okay, so what I want to do is just draw my draw this sigma omega by sigma t as a function of omega. Okay, so we considered these various regimes, right? The first was the Rayleigh regime at low frequencies, which gives you omega to the power of 4, right? And then we considered, so you know, this is some omega naught. Okay, or we actually write it as omega by omega naught. So the x-axis is actually normalized to omega naught. So this is oh man. So this is like 1, right? So this is the resonance, and at omega much greater than omega naught, it sort of flattens, right? This is the sigma t equals 1. This is 1, right? And so this is my resonance, where the cross section is enormously high, right? Because you can actually see, go up at omega close to omega naught, this is really a delta function. So you have this Rayleigh-Taylor part, and then you have a resonance where it is Lorentzian, and then it saturates to sigma t, right? And this is 1, and this is Rayleigh-Jeans, this is Thomson, this is Lorentzian. Right, one thing that you may notice is that when I did this integral, sigma from 0 to infinity, sigma omega d omega, right? If it saturates to sigma t at large omega, in fact, this integral should really diverge. It should give an infinity, because you're integrating over infinite frequencies, a constant number which is sigma t. But the point is, beyond certain frequencies, right, this radiation reaction approximation that it was perturbative breaks down. Okay, so that's why this integral actually does not just go from 0 to infinity, it goes to this frequency where this assumption breaks down. Let's call this omega max. Okay, and when does it break down? It breaks down, so radiation reaction force breaks down when at omega max is equal to 1 by tau. And if you recall, tau was this light crossing time across an electron, which is extremely tiny, 10 to the minus 23 seconds. So you know this whole thing breaks down beyond that. So this integral actually should really not be to infinity but to omega max. Okay, in that case, what is the value of this integral? So sigma t times omega max is what's contributed by the area till this point. Okay, and the claim is that this is much less than pi 2 pi square e square by mc, and omega max was 1 by tau. So basically the point is sigma t omega max is much less than sigma t by tau, right? Because omega max is, this is where it is valid, and this is nothing but 4 pi e square by mc. Or in other words, sigma, this integral, is actually not dominated by, is actually dominated by this Lorentzian peak and not by this portion. Of course, if it went out to infinity, it should diverge, but this radiation treatment breaks down. So, okay, so this is sort of concluding this class, but the important things to take away from this class is that we constructed this classical model for formation of lines, which gives rise to a Lorentzian, and that's that's the standard harmonic oscillator model. And we then also considered a driven harmonic oscillator model for scattering. Okay, and this is valid. This is valid in general, not just for high frequency, for example, like in the Thomson regime. It's also valid in the low frequency regime, the Rayleigh regime. It gives you the correct omega to the power of 4 behavior. And it's also valid close to the resonance, omega close to omega naught, where the scattering profile is identical to the natural line profile for emission. Okay, so this actually concludes our chapter 3 from the book. Okay, so please read up, and from the next class we will start with chapter 4, which is relativistic treatment of particles and radiation. So I encourage you to brush up your relativity a little bit. Okay, anything else? I will stop.
Sir, can you once again explain
Yes.
the omega max derivation, how we got
Just
that?
okay, let me go back. Right, so omega max is the frequency at which your, this is the maximum value of omega at which your radiation reaction treatment, the perturbative treatment, is valid. And basically omega max is much less than 1 by tau, and this tau was this your radiation, the light crossing time across an electron. So what I sort of argued was that this is basically the, the area under the curve till omega max. This is much less than this guy. This is what I have to argue. Well, I did not really derive it, I just motivated it, but it will actually be good to check that this indeed comes out to be true. So omega. Yes.
No, so my question is omega max, is sigma t omega max equal to that 4 pi e square by mc, or is it that sigma t by tau equal to that quantity?
Sigma t by tau is equal to that, and
okay.
Much small compared to this, right? So tau, right? Sigma t was 8 pi by 3 r square, and tau was r naught by c. So this is equal to 8 pi by 3. R naught was e squared by mc squared times c, right? I'm missing a factor of 2, but you get that, right? You get 8 pi by 3 e squared by mc. So that's this. But the point is, omega max has to be much less than 1 by tau for this treatment, and the area under this portion is at max comparable to this. So that's why this does not blow up. The point was this does not blow up.
Okay.
Because formally it looks like it should blow up because it goes to sigma t at large frequencies, right? But the point is this treatment breaks down, and this radiation reaction force that you have here, this expression, is no longer valid. So this has to be treated quantum mechanically with QED. Okay, and it turns out that in that case this will not contribute much. Okay, so this was actually the point. Okay, anything else?
Thank you, sir.
Yeah, so now we'll start with the chapter 4. So I'll stop recording.